Have you ever looked up at the stars and wondered, what would it be like up there? People have been exploring space for decades. Technology keeps advancing and literally propelling us further beyond the Earth's atmosphere. Today on the WPI Podcast, we're talking about how things like satellites and human missions get to space and move around once they do. This episode is all about propulsion. Hi, I'm John Kane, and this is your home for news and expertise from the classrooms and labs of Worcester Polytechnic Institute. Today we'll explore advances in aerospace propulsion over time and the future of electric propulsion. WPI is a great place to have this conversation. We're really proud that one of our alums was the father of modern rocketry. Robert Goddard graduated from WPI in 1908, and he made history in 1926 by launching the world's first liquid-fueled rocket. And today that skyward spirit of innovation and pushing boundaries continues. WPI students and professors are doing research in aerospace engineering, including propulsion. So let's blast off. Our guests today are Nikolaos Gatsonis. He goes by Nikos. He's professor and head of the Department of Aerospace Engineering at WPI. And John Blandino, a professor in the Department of Aerospace Engineering here. He previously worked as an engineer in the Advanced Propulsion Technology Group at NASA's Jet Propulsion Laboratory. They study spacecraft propulsion and lead research in electric propulsion. John and Nikos, I'm so happy to have you here. Thanks for being on the WPI Podcast.
I'm glad to be here.
Thanks for inviting us.
John, I want to start with you for a few questions.
Sure.
We're talking in 2026, and it's 100 years after Robert Goddard made history not far from here in Auburn, Massachusetts. That's where he successfully conducted the first ever liquid-fueled rocket launch. Tell us a little bit why this was so groundbreaking.
Yeah, so I think a good place to start maybe is just with a little bit of background in terms of what a liquid-fueled rocket is and how it's different from, say, a solid-fueled rocket.
Mm-hmm.
Rockets for fireworks had been around and in warfare for thousands of years. And any kind of a chemical propulsion system or rocket, like we're going to talk about today, the energy that comes to accelerate the gases to high velocity is stored as chemical energy. The way engineers do this is use the combustion process between a fuel and an oxidizer. In a solid rocket motor, the fuel and the oxidizer are both stored as solids. So that has some advantages, but it also has some important drawbacks. And in a liquid fuel rocket, the fuel and the oxidizer are stored and supplied as liquid. And even at Goddard's early work, recognize many of the advantages of this. Just to list a few, the ability to start and stop throughout the flight, the ability to meter the propellants individually, so you can control the fuel to oxidizer ratio in a way you can't do easily with a solid rocket motor, allows you to tailor the thrust characteristics for your particular flight. So this first flight in 1926 was quite groundbreaking in that it was the first time that we know of that a controlled flight using the ability to reliably ignite and meter and control the fuel and oxidizer to achieve that.
And liquid fuel rockets are used a lot. If people think today, is that the technology that's used on a lot of the rockets that NASA uses to get to space?
Yes, absolutely. We're going to talk about a lot of different propulsion systems. But to get off the surface of the Earth, to get off the Earth's gravity well, we rely on high thrust propulsion systems, which you really can only achieve with chemical propulsion, either usually liquids, liquid hydrogen, liquid oxygen, and rocket fuel, which is a kerosene derivative, and also solid rockets, like the space shuttle had a combination of liquid hydrogen, oxygen, and the strap-on solid boosters.
Obviously, Goddard was known for developing rockets to blast off from the ground, but he also had an eye on pushing the envelope a little bit further. He envisioned a future of moving spacecraft using a different type of propulsion, electric propulsion. I'm wondering if you could tell me what that is, John.
Yeah, so we were just talking about chemical propulsion. And in chemical propulsion, as I said, the energy is stored in the chemical bonds. Some propellants are much more energetic than others. They're more dangerous to handle, et cetera. But ultimately, the most energy you can extract per pound or per kilogram of propellant comes fundamentally from the chemical makeup of the fuel and the oxidizer. Mm-hmm. With electric propulsion, we rely on an electrical power source to produce and accelerate the exhaust gases. The main advantage is that essentially the velocity and the exhaust, the thrust that you can achieve is limited really only by the power you have available. So you're providing an external electrical power source. And engineers, we divide and think of electric propulsion systems kind of in three different categories depending on how you use the electricity to accelerate it. There's something called, we call electrothermal, which is where you take a gas and you heat it electrically, kind of like you might heat tea in a teapot, and then vaporize it and accelerate it through a nozzle. So you're still using a nozzle to convert thermal energy to kinetic energy, but you're achieving the heating through electrical means, not chemical means. A second category would be electromagnetic, where we use a combination of electric and magnetic fields. If you think of a drill or a motor or any kind of an electric motor, you have a stator and a rotor, you applied electricity, the current is flowing through a magnetic field that causes the winding to spin. If you think of instead of a winding, if these charges and current were being carried by charged particles, they're free to accelerate. And then the third category is what we call electrostatic. So this doesn't rely on magnetic fields primarily for acceleration, although there's still magnets used for production. This is not unlike what some people will remember in cathode ray tubes and old-fashioned televisions, where we would accelerate electrons to high velocity and they would hit a phosphor screen and you'd see an image. Oscilloscopes and old televisions used to do this. So even as a student here at WPI, Robert Goddard was writing in his diaries speculations about accelerating charged particles to react to produce thrust in a rocket for space travel. So He was way ahead of his time.
Wow, I'd say so. You started to talk about this, John. So what are the strengths and what are the weaknesses of electric propulsion?
The biggest and probably the most significant advantage of electric propulsion is that you can achieve high exhaust velocity. The higher the exhaust velocity for a given mass of propellant, and propellant includes both fuel and the oxidizer. We use that term for both. So if I have a kilogram or a pound of propellant, the higher the exhaust velocity, the more mass that I can deliver to a certain final velocity. I guess the first answer to your question as an advantage is that once you get out of the Earth's gravity well, which is where electric propulsion is used, NASA for its long range missions to other planets and ambitious missions to asteroids and comets, getting mass off the surface of the Earth is very, very costly. Dollars as well as energy. And so we use electric propulsion once we're in space so that we can get more bang for the buck, more mass delivered to our destination with a given mass that we've gotten off the surface of the Earth. Now, some of the disadvantages are that the higher the exhaust velocity for a given amount of power, the lower the thrust. So the practical implication of that is that these missions that NASA has that use electric propulsion, the thrusters might be on for months, weeks and months at a time. And the velocity slowly builds up over time. It's doing it more efficiently, but it takes a long time. If you're looking at piloted missions to Mars, where you have to rescue a crew, or something where time is urgent, and that's an important factor, then that might be a limitation. And one last one I'll mention that Robert Goddard was not aware of yet, the understanding of this, is something we call the power supply penalty. And what that is, to produce, we haven't gotten into the physics and the mechanics of how you accelerate particles, but you need electronics, you need high voltage power supplies and so forth.
Right.
So to produce a very high exhaust velocity, which you certainly can, but you have to carry along a power system to do that. And there's a penalty for that. So you end up spending more of your mass to have a power system to give you the high velocity than maybe you would have if you just used a chemical system to begin with. And so there's a trade-off.
Certainly a lot of factors to consider for each individual mission. So John, let's talk a little bit more about Goddard. What did Goddard specifically say about his hopes for electric propulsion and how it could be used?
When Goddard was an undergrad here, he wrote prodigiously in several notebooks that he kept, which are currently in the archives at Clark. He was reading papers that were coming out he was a physics student, and he was certainly aware of work that was being done primarily in England with something called a Crookes tube, which is a device that was invented to allow the study of so-called cathode rays, which were electron beams, essentially, predecessors to our cathode ray tubes, kind of. And so this is where he was learning about these devices that could accelerate particles to high velocity. But in his speculations, as he called them, these entries in his notebooks, he looked at not just propulsion, although that was his primary area of contribution and where he put most of his attention. But he looked at many different aspects of spaceflight. How would a spacecraft survive meteorite impacts? How would a crew survive? He really was thinking of all sorts of dimensions of the problem. So to your question of how did he see electric propulsion fitting in, first of all, he didn't conceive of it yet as electric propulsion,
Sure.
but he recognized the value of accelerating particles to high velocity. He saw the ability to use electricity to accelerate particles to high velocity as a way to mitigate some of these problems with extended time for travel in space and some of the other issues. He was really looking for all sorts of things that would improve space travel. I think it was 2 patents that he received, and in particular, the second one in 1920 really laid out what is considered to be the first documented description of a electrostatic ion thruster. And basically, it was a device that would allow the acceleration of charged particles, not just electrons, but positively charged atomic ions, to a high enough velocity to produce thrust. Goddard recognized the need for neutralization. If you're a spacecraft in space and you're spitting out positively charged particles, your spacecraft is going to build up a very negative potential. So it's kind of like a capacitor for anybody who's familiar with electronics that's just being discharged or charged. And so he recognized that need. So that was a pretty groundbreaking description. Another item that was either in that patent or the one that was earlier was a description of how to use magnetic fields to improve the ionization efficiency. This is the process where you create the ions that you want to accelerate. Mm-hmm. And that also previewed what now we use commonly in electron bombardment ion thrusters, which is a very commonly used type of ion thruster where you use electrons to collide with neutral gas atoms to produce ions, which you then accelerate.
If folks are interested in learning more about Goddard's time at WPI, there's a digital exhibit that WPI's Archives and Special Collections has available. We'll have a link in the show notes. Nikos, I want to bring you in here, and I want to ask, has the dream of Goddard's become a reality? Are we there yet when it comes to his vision for electric propulsion specifically? How is electric propulsion being applied today in space?
John explained already some of the elements that we saw on Goddard's writings. And they had to do both on the electrostatic devices, the ion thrusters, but also the law of magnetic fields. And both of these are present today in the technologies that we mainly use for space propulsion. And I just want to make again the distinction that we're talking about in-space propulsion. Mm-hmm. So we're not accessing space, but we are there because of Goddard. And now we're using again some of Goddard's ideas to manipulate the spacecraft in space. When I graduated from graduate school, it was in 1991. And at that time, electric propulsion was primarily a subject of research. Mm-hmm. So in the 90s, NASA would have laboratories where they were working on electric propulsion, and the Air Force, they had a footprint on that, and some companies had started working on electric propulsion, but it was not a technology that was readily available or flown on spacecraft. So where are we today? First, let's say where do we do business in space, right? We do business in what we call LEO, the low Earth orbit. And these are the orbits above 300 kilometers, roughly up to 1,000 kilometers altitude. Mm-hmm. In low Earth orbit, the things we do with electric propulsion, we do what we call station keeping. We keep nudging the spacecraft while they're in orbit. We also do orbit correction. Sometimes we may do some orbit raising. We also can do deorbiting at the end of life. This is a major issue with the space debris. So provisions now are for spacecraft to deorbit safely and disintegrate, right, during reentry. So these are the 3 main functions that spacecraft propulsion systems do in orbit, and we can do them with electric propulsion. Mm-hmm. So today, Starlink uses entirely Hall thrusters in order to do all of these manipulations for the constellation they have in low Earth orbit. So it's a major dream come true, even for when I was in 91, and Hall thrusters were practically back then not very well known in the United States, right? So it was technology that was developed after that. Now, the next place where we use electric propulsion and where we do business in space is what we call geostationary Earth orbit, GEO. This is where we have most of our communication satellites. In geostationary orbits, the spacecraft stays stationary about a point on Earth because roughly its period is 24 hours. But you still need to nudge them around. Constantly we turn our thrusters on, etc. The other major maneuver, if you wish, we do in geostationary orbits is moving them from insertion, right, to a geostationary orbit. Remember, I said low Earth orbit is about 300 kilometers. So when we launch and we want to reach geostationary orbit, we put our spacecraft in something that looks like an ellipse. And this ellipse has one side close to Earth, right, about 300 and something kilometers, but the other is close to geostationary orbit, which is 36,000 kilometers.
Okay.
Think about it, right? Pretty much a third of the lifetime of a car's a lifetime. So now electric propulsion can take the spacecraft and slowly spiral, as John explained, right, with this very small thrust, constantly nudging, and then in a few months you reach your stationary orbit. Do you care about the time? Absolutely not, because these assets are supposed to be there for 10, 15 years and more. So that's how we move them. So now in geostationary orbit, we have companies that provide to you the option. It's like when you buy your car, you can buy a hybrid, you can buy an electric and all-electric, you can buy a classic combustion car. And you have a number of spacecraft in GEO now that fly electric, and some of them are what we call all-electric. And then we have the one-of-a-kind missions, which are the so-called deep space missions. We had deep space missions which flew electric propulsion spacecraft. For example, Dawn, it flew ion thrusters, right? And Dawn did things that we could not do with chemical propulsion. The Dawn spacecraft visited Vesta, which I believe is a protoplanet, and then it made a very peculiar turn, and in a few years, it visited Ceres. Yeah. And Ceres is a dwarf planet. And I think that maneuver, you could not do them with chemical propulsion. You can only do it with electric propulsion. And then finally, the last class of missions we have is what we call technology demonstrators. And technology demonstrators is where we push the technology to the next level. And there are several technology demonstrators today that plan to use electric propulsion, or they've used them recently, right? 2025, we had the launch of a small spacecraft, a CubeSat, which used a pulse plasma thruster. I'm going to talk a little bit about them later on. These CubeSats are released from the space station. So I think Goddard would be ecstatic to see where we have been. But it's also remarkable to see that his concepts, both for electrostatic propulsion and also using magnetic fields, not only to ionize gas, but to produce thrust, it's part of what we're doing today.
So I'm very curious now, what is the research that you both are doing here at WPI to sort of push this technology even further?
Yes, I mentioned before the pulse plasma thrusters. These can be considered electrostatic or electromagnetic because they use both electrostatic and electromagnetic forces to accelerate gases. And how to produce these gases with these pulse plasma thrusters? First of all, the propellant is solid Teflon. The Teflon that we used to have on our frying pans. And in simple terms, you have a capacitor and you strike an arc on the surface of this bar, right, which is Teflon, and you ablate and then you ionize little portions of this Teflon material. And that is accelerated in small pulses, and that produces thrust. This is a PPT in short. Now, PPTs were flown in two missions, one in the 60s, and then one, they flew on a Nova spacecraft in 81, I believe. I joined WPI in 94. At that time, somebody realized that this device is so stable that it doesn't need propellant management. It has this Teflon bar that it's right there, and they had it on a shelf. They turned it on, and it produced thrust. So wonderful, stability and simplicity, right? You reduce all of your plumbing. There's nothing to worry about. So there was a renewed interest, not only for that reason, but for other reasons. In 1996, I received my first support from NASA to study these pulse plasma thrusters. And those studies involved various aspects of these devices because we did not really understand how thrust was produced, for example. So there were open issues on how they operate and also how to optimize them, how to make them better. And these studies involved modeling, simulations, and also involved experiments, which I used to do with my students who would go at NASA. At the same time, the ecosystem around this technology evolved. Companies started investing into this technology. Primex, for example. 2001, we had the first flight of a pulse plasma thruster with a tech demonstrator, which we call the EO spacecraft. So EO flew with this technology that a lot of us contributed, including myself. Now, moving forward, where do we go after that? With that technology, and I had students who were involved. At the same time, a company here in Massachusetts called Busek, they're part of the large push for the Artemis plan, started developing technologies for electric propulsion. A lot of my students went to that company. So when they went there, we started looking into a different type of a pulse plasma thruster now, which is in the shape of a cigar, but of much thinner. It's a cylindrical. We call them coaxial pulse plasma thrusters. So from this larger device that had this block of Teflon, we went to something which is very, very thin, right? A cylindrical. But now we had to develop, again, the understanding of how they work. And those would be primarily very good for spacecraft that at that time started becoming smaller. Mm-hmm. The era of micro spacecraft, right? And small sats coming into the play. So we were looking into technologies that would fit into that part. So it took us a few years to work on these thrusters again, micro thrusters. And then in 2007, Busek flew this thruster on board on a small satellite, the Falcon Sat-3, which was developed with funding from the Air Force. So from the NASA ecosystem, now the Air Force becomes a player. So you see how technology, right, develops. We move to the next one.
Always iterating.
Always right. And then after that, we tried to do something completely different. And this time it was work that I was doing with Johns Hopkins University Applied Physics Lab. Now we took this thruster and we make it a micro-scale device. We took now a case where the thruster now is miniaturized. It's a microsystem, and it works with water. And it has a very tiny hole on micro-scale where you use it, right, for different propulsion technologies. So we worked for a few years on that technology as well. I moved into other levels of technology, but there is a push and pull in technology. And as we push the envelope, we need to build our tools that range from experiments, the experimental tools, and also modeling and simulation tools. And I mentioned before that come 2025, others develop different types of propulsion devices, but the quest is still going on.
Yeah, I'm noticing some themes there, the push for smaller and the need to constantly meet the demands of the marketplace.
So Nikos has just explained the pulse plasma thruster.
Mm-hmm.
So an example of a different type of electric propulsion technology, earlier I mentioned in the context of some of Goddard's recognition that a spacecraft needs neutralization, otherwise it builds up a charge. So electron sources, which you can think of as a subcomponent of an electric thruster, is a significant part for electrostatic thrusters in particular, for ion and Hall thrusters. And so one of the things that we just finished up a multi-year project jointly with this company, Busek. And this was a project for the Air Force looking at radio frequency-driven electron sources. We call them cathodes. Now, why is that important? This circles back to one of your earlier questions about the advantages of electric propulsion. And another advantage is that whereas with a chemical propulsion system, you're limited to certain propellants that have high energy content, at least in principle, with electric propulsion, you could use different gases, different propellants. Mm-hmm. And this is, in fact, resulted in a lot of interest from a lot of different constituencies. So, for example, the Air Force is particularly interested in a number of different propellant options. And one of them is, for example, for electric propulsion that would fly in very low Earth orbit and ingest the atmosphere at those altitudes. We're talking maybe 200 to 300 kilometers. These are altitudes where a spacecraft would normally deorbit after a few days. But the Air Force is looking at using essentially a way of collecting that atmosphere and using it, essentially you're breathing the air in the atmosphere to produce your fuel.
Wow.
So to circle back to what we were doing here, if you have one of these cathodes, these electron sources that can use air, for example, and the air composition in low Earth orbit is not the same as it is at sea level. So that's one thing. NASA is also interested in alternative propellants. They've looked at missions where, in principle, if you have a science mission on Mars, you can use the Martian atmosphere, which is mostly CO2, and you can produce propellants from that. So the ability to use different propellants is a major driver. So this project that we've been working on uses a radio frequency discharge. Essentially, it's a way of ionizing the gas to be able to extract electrons, to neutralize the beam produced by a thruster, and also to create the ions that you would accelerate to produce thrust. So it's another dimension to electric propulsion, is the ability to use different propellants. One of the advantages of this, obviously, is that you don't have to carry as much propellant because you're breathing it up there. But the other aspect of this is that this allows you really two things other than not bringing propellant. It allows you, in principle at least, to fly to lower altitudes than otherwise would be possible. Because rather than essentially from the drag of the atmosphere, losing orbital energy and deorbiting in a very short period of time, probably measured in days, if you're actively producing thrust by collecting propellant from the atmosphere, you can provide thrust to counteract the drag and stay aloft for an extended period. You can fly to lower altitudes and you can extend your mission life. And this is important clearly for defense reasons, because you can loiter at lower altitudes, you can do imaging with smaller cameras, but also for environmental satellites, Earth resource monitoring, a whole range of applications in terms of basic science and studying those parts of the atmosphere, which up until now primarily have been accessible through the use of sounding rockets, which have a very limited residence time at these altitudes.
Right. There is another area which is equally important, and that has to do with the way we integrate electric propulsion devices with spacecraft. And these issues of integrations do not only relate to electric propulsion devices, but also to chemical thrusters. You have a thruster that produces a plume. And in the vacuum of space, these plumes behave in different ways, whether they are neutral plumes or ionized plumes. Because in space, if you are in low Earth orbit, the plumes will interact also with the magnetic field of the Earth. The issue of integration means what is the potential of the plume to damage surfaces or to coat surfaces or to interact with sensitive instruments that we carry on spacecraft. Mm-hmm. So that's another area where we have been doing a lot of research at WPI. And that involved the modeling initially, and then we branched also to include experimental aspects. Currently, we're looking with the Air Force into how the solar environment interacts with the solar arrays that we carry on board spacecraft. We mentioned, for example, the need for more power in space. And more power means solar arrays that operate at different levels than the solar arrays that we have on a small CubeSat. So all of these accentuate the need to understand how systems themselves interact with the environment, but also how systems interact with the plumes that we generate from electric propulsion devices. And I did work on that with funding both from NASA and Air Force, where we develop now very highly accurate simulation codes in order to model these very complex environments. So all of this come into this area of what we call integration of electric propulsion on spacecraft, where we're very active. This became what it is because now we have a very well-organized laboratory which goes from experiments to simulation and also includes both the devices. We mentioned some thrusters that we worked on, subsystems that go into the thrusters, the cathodes, the hollow cathodes that John mentioned, but also now the integration of these devices on functioning spacecraft.
Yeah, very important questions, pulling the whole picture together. Nothing operates in a bubble. So would it be fair to say that electric propulsion provides the opportunity to do a number of things, make the spacecraft more efficient, reduce the cost associated with space travel, allowing us to go to places where maybe we couldn't get to before with the need for less fuel and propellant.
And when prior to coming, I started at WPI in 2001. So prior to that, I had been about 12 years at the Jet Propulsion Lab. So the charter for JPL is primarily robotic exploration of deep space. And what you're referring to is absolutely true. We would refer in many cases as electric propulsion being mission enabling. That was the terminology, because you just cannot do it otherwise. To explore Jupiter's moons and to send probes that would spend any length of time or deliver any reasonable payload to Saturn or beyond, you really have to do it with electric propulsion, because otherwise you just have too much of the mass you can launch is propellant, and then you don't have enough for your payload.
Gotcha. Nikos, I wanted to ask you about this. You both have talked a lot about some incredible work going on in the lab. I'm wondering, how does this work get from WPI's labs out into the world, or more accurately, space?
Okay, I'm going to talk both about the world and also the space. First of all, the work that we do here is funded research, and it's funded by different government agencies or industry. The work that we do with government usually is fundamental research and basic research, and this is where we do the push in the technology. And the work we do with industry, where we collaborate in proposals, and they have to do with specific technology. And the technologies are classified in what we refer to as TRL levels, technology readiness levels. So usually the research that we do, which is fundamental with government, is at low TRL. We take visionary things and we try to push and understand. And then higher TRL works with companies. So a lot of the things we do now, they find all these venues. Now, the other way with which we reach the world is through our students, because we graduate students who have done work on electropropulsion. So these are also ambassadors where they really push the envelope when they go out there. And in some cases, some of these people became leaders in these technologies within the companies that we're working on. Now, reaching to space to do it indigenously here requires capabilities that we don't have ourselves, right? But we do that in collaborations with others, and that's our way of reaching the space. We've also participated in the past, and we hope in the future too, in space experiments. When we mentioned, for example, the integration issues. I worked with Johns Hopkins University in a series of space experiments when we basically were launching these ionized plumes in space, and we were monitoring them to see exactly how they interact with magnetic fields. So that's the way we reach space.
I'd love to paint a picture for folks about what does it look like in the labs? How do you do this research?
Yes, on electric propulsion in particular. And that involves modeling, simulation, and experiments. In modeling and simulation, I can give you the picture, but includes a lot of paper and pencil where you do modeling, and then a lot of simulation where, again, it involves high-performance computing. And we have our own clusters where we do this simulation work, but we always tied to experiments. And for experiments, John is the best person to talk about.
I guess a major distinguishing feature of research with electric propulsion, charged particles, electrons, ions, and so forth. And to produce these and to accelerate them requires very well-controlled environments. In other words, there's no way that we could reproduce the environment in one of these thrusters here at atmosphere. It completely changes the collisional behavior, the regimes that you're operating in, and so forth.
So you've got a challenge on your hands.
Yeah, so something that's ubiquitous with any laboratory that does work in electric propulsion are the vacuum chambers. And essentially these simulate the vacuum of space and in our devices and so forth. And so we have a number of these here at WPI. These are chambers that typically using a series of different pumps. So we use those and we produce the environments we need, and then we have our apparatus in there. We can supply the gases we're testing to simulate the propellants. And we have a wide variety of instrumentation to measure electric potentials or voltages, currents, and so forth.
I just want to add something that making measurements in these propulsion systems is not trivial. And very often, we have to invent new diagnostics. And the diagnostics become then the object of investigation. We have a whole series of theses where we develop specific diagnostics in order to measure something. And it has to do not only with the complexity of the plasmas, that's how we call them, that we generate with electric propulsion devices, but also a lot of times it has to do with the size. You mentioned before the miniaturization. Yeah. If you want to measure plumes that are of millimeters in diameter, you need to develop new techniques. And both John and I have been working also on development of diagnostics.
Maybe speak specifically to maybe a prospective student that's listening to this and they've heard about some of the cool equipment and some of the cool simulations that they could do here. What are some of the ways that students directly participate in this work during their experience? Nikos?
Students will find that the WPI, it's one of the places in the United States, one of the university laboratories where they can pursue work in electric propulsion and electric propulsion integration issues. And we have the ability to allow students from all the way, the undergraduate, all the way to postdoc level to work on these technologies. Undergraduate students can work on electric propulsion or integration issues by doing their senior thesis project, which is the major qualifying project. Now, at the master's level and PhD level, we have funded projects and we have students who work on master theses and PhD dissertations. We also have availability of projects. We call them directed research for students who pursue the non-thesis master's option, and they can pick smaller bits of research. And you can find those students working in our labs all the time, both experiments and computations. And because our groups work together, John and I work together, our students are often all together and they understand all the tools of simulation technology, but also the experimentation. We have also postdoc possibilities. I've hosted several postdocs. Some of them are now faculty in other universities. So we have the entire ecosystem. So we can tackle now more complex issues associated with electric propulsion and integration.
Sounds like great opportunities for students. Well, Nikos and John, thank you so much for sharing your insight about Goddard, about propulsion, about electric propulsion, and the work going on here at WPI and the opportunities that students have to join you in pushing forward on space technology. Thank you so much for being on the WPI podcast.
Thank you, John. It's been great to be here.
Thanks for inviting us. It was wonderful.
Nikolaos Gatsonis is a professor and head of the Department of Aerospace Engineering at WPI, and John Blandino is a professor in the Department of Aerospace Engineering. Thanks to you for listening to the WPI podcast. Please follow us wherever you get your podcasts. We're now on Pandora, so check us out there. As always, you can find us at wpi.edu/listen. On that page, you'll find all our episodes, other podcasts from across campus, and audio versions of news stories about our students, faculty, and staff. You can get WPI News anytime by asking Alexa to open WPI. I'd like to thank computer science and music undergraduate student Aster Detweiler for the audio engineering help. Tune in next time for another episode of the WPI podcast. I'm John Kane. Talk to you soon.